All right, here are the notes for section 6.1 and 6.2. So our review preview. The main objective of this unit is to develop the ability to conduct hypothesis tests for claims made by population proportion P, population mean mu, or population standard deviation sigma. So we'll start with the basics of hypothesis testing. So in statistics, a hypothesis is a claim or statement about a property of a population. A hypothesis test, or a test of significance, is a procedure for testing a claim about that property. So we do have what's referred to as the rare event rule. The rare event rule of inferential statistics says that if, under a given assumption, the probability of a particular observed event is extremely small, we conclude that the assumption is probably not correct. So if we make an assumption and then calculate the probability of that assumption happening, and it's only like 1% of the time, our assumption is probably incorrect. Okay, so here we have the methods for which you can do some hypothesis testing. So there's a method that involves the p-value, or what's referred to as the critical value. So for p-value method, step one, identify the specific claim or hypothesis to be tested and put it in symbolic form. So that's the same for both of these. Step two, give the symbolic form that must be true when the original claim is false. So you're finding the opposite thing. So, if our claim is that x is less than 2, symbolic form would be x is greater than or equal to 2. So what would make my statement false? So for 3 of the 2 symbolic expressions obtained so far, the alternate hypothesis H1 be the one not containing inequality, so that H1 uses the symbol less than, greater than, or not equal to. Let the null hypothesis be the symbolic expression that the parameter equals the fixed value being considered. So same thing over here. So for 4, you need to select a significance level alpha based on the seriousness of a type 1 error, which we'll talk about later. Make alpha small if the consequences of rejecting H0 are severe. Usually you use 0.5 or 0.1. 0.5 is the most common one. All right, identify the statistic that is relevant to this test and determine its sampling distribution. So is it normal, is it t, is it chi-squared? All right, so 6, find the test statistics and find the p-value. Draw a graph to show the test statistic and the p-value. Find the test statistic, the critical values, and the critical region. Draw a graph and include the test statistic, the critical values, and the critical region. So this is where they start being different. Reject H0 if the p-value is less than or equal to the significance level. Fail to reject H0 if the p-value is greater. Reject H0 if the test statistic is in the critical region. Fail if it's not in the critical region. So, okay. Restate the previous decision as simple, non-technical terms, and address the original claim. So there's all the steps. So now we kind of break down how to get through those steps. So steps 1, 2, and 3, use the claim to create a null hypothesis and an alternate hypothesis. So null is H0, alternate is H1. Identify the null hypothesis and alternate hypotheses so that the formal hypothesis test includes these standard components that are used, often many different disciplines. So null hypothesis, H0, statement that the value of the population parameter such as proportion, mean, or standard deviation is equal to some claimed value. The term null is used to indicate no change or no effect or difference. We test the null hypothesis directly in the sense that we assume or pretend that it's true and reach a conclusion either to reject it or fail to reject it. Now, if you notice, these words are kind of important. We can reject it, which means that we say that it's false. Fail to reject doesn't say that it's true, just means we can't say that it's false, and that's not actually the same thing. All right, the alternative hypothesis, H1 or HA or H capital A, state the parameter has a value that is somehow differs from the null hypothesis. For a methods unit, symbolic form must use less than, greater than, or than not equal to. All right, so step 4, significance level. Identify the value of the significance level alpha so that we have a specific criterion for distinguishing between sample results that could easily occur by chance and sample results that are unlikely to occur by chance. All righty, so step 5. Identify the statistic relevant to the test and determine its sampling distribution. So it says normal, t, or chi-squared. So based on the sample statistic that is relevant to the claim being tested, identify the sampling distribution so that the correct sampling distribution can be used. So if we are testing the proportion, p, we're going to use a normal distribution. Our test statistic is the z-value. If we're going to test the mean, we're going to use t. If sigma is not known and we know it's normally distributed, or sigma is not known and we know they have more than 30 measurements. So there's our t-value. We can test the mean using the normal distribution if we know the standard deviation and it's normally distributed, or we know the standard deviation and we have more than 30 measurements. So there's our z statistic again, a little bit different because this one deals with proportion, this one deals with the mean, standard deviation or the variance. That's a chi-squared. So normally distributed population has to be normally distributed, and there is our equation. Okay, so step 6, find the value of the test statistic. So that means we're going to plug our values into these far right columns. So transform the relevant sample statistic to a standardized score called the test statistic. Then find the p-value that can be used to make a decision about the null hypothesis or find critical values, so on and so forth. The test statistic is a value used in making decisions. It is found by converting the sample statistics, such as proportion p, sample mean x bar, or the standard deviation s, to a score z, t, or chi-squared, with the assumption the null hypothesis is true. Okay, so tests of hypothesis, two-tailed, left-tailed, right-tailed. So the critical region or rejection region, so if it falls into this critical region, we reject H0, corresponds to the values of the test statistic that cause us to reject the null hypothesis. So a two-tailed test, there are two extreme regions or tails under the curve. Sign used in H1 is a not equal sign. Left-tailed test, the critical region is in the extreme left under the curve. Right-tailed test in the extreme right. So if you think about the normal curve, for two-tailed, there would be two rejection zones on the sides. Left-tailed test, that's a really bad bell curve. The critical region is on the left, and right-tailed test, the critical region is over here on the right. So if our test statistic falls out here, we reject H0. Okay, so p-method or critical value. So p-value method, find the p-value, which is the probability of getting a value of the test statistic that is at least as extreme as the one represented in the sample data, assuming the null hypothesis is true. To find the p-value, first find the area beyond the test statistic, then use the procedure below. So critical region in the left tail, the p-value is equal to the area to the left of the test statistic. Critical region in the right tail, p-value area to the right. Critical region two tails, p-value equals twice the area in the tail beyond the test statistic. Okay, so critical value method. Critical value method, or a traditional method, we find the critical values, which separate the critical region, so that's where my dashed lines are up here, from the values that do not lead to rejection. Critical values depend on the nature of the null hypothesis, the sampling distribution, and significance level alpha. So we're probably going to be using the critical value method here. All right. Whew, a lot. Step 7, make a decision. So reject the null hypothesis, fail to reject. So for the critical value method, if the test statistic is in the critical region, reject H0. If the test statistic is not in the critical region, fail to reject H0, which is not the same thing as saying that H0 is true. It's just saying we don't have enough information to say for sure that's false. Okay, so step 8, restate the decision using simple, so that's kind of rewrite it. All right, final conclusion. The original claim does not include equality and you reject H0. There is sufficient evidence to support the claim that original claim does not include equality and you fail to reject H0. There is not sufficient evidence. Including equality and you reject. There is after rejection of the claim, there's not sufficient evidence to reject. Okay. Okay, so let's finally do an example here. So example 1, assume that 100 babies are born to 100 couples treated with the X sort. There we go. Method of gender selection that is claimed to make girls more likely. 58 of the 100 babies are girls. The test to claim that with the X-sort method, the proportion of girls is greater than the proportion of 0.5 that occurs without any treatment. Use P to denote the proportion of girls born with the X-sort method and test to claim that P is greater than 0.5. Okay, so let's see here. Let's see what we got. So H0 includes the equality. No, don't want an equal sign there, so colon. P is equal to 0.5. The alternate hypothesis is the one that includes the inequality, so we have that. Okay, so, oops, got ahead of myself. Doop-a-doo. Sorry. Okay, so let's see here. We are doing a proportion, right? No, we need a bunch of stats here. Okay, so oops, let me find my notes. So I need my rules for proportional testing. Okay. So we're testing a proportion, so we're going to calculate a z-value. So let's see here. Our p hat is going to be 0.58, the proportion in our sample. Minus p, which is 0.5, over the square root of p times q all over n. There's 100 people. Let's get my calculator out so we can get our z-score here. So 0.58 minus 0.5 over the square root of 0.5 times 0.5 divided by 100. So we get a z-score of I think I typed it in my calculator wrong. Should be 1.6 here. So let's see here. So now depending on, so we got some critical region up here. So depending on where we set this critical value, we can actually reject it or sorry. So we can set this value. Normally it's, so here's our failure region. Since we have a greater than, it's off the tail. So if our z value here falls in this region, depending on where we set our z-score here, is we can either reject or accept this. So let's see here. And usually we're going to set this bar as 1.645, I believe. So our z-score actually falls in this region. So we fail to reject H0, which means that that proportion could happen. No, the claim that p is greater than 0.5 is false. We reject this, accept that, or we fail to reject the null hypothesis. So we're saying that this is, it could be that that's entirely due to chance. The proportion actually is 0.5. Okay. So we've also got then errors in hypothesis testing. So there are two types of errors you can have. You can have a type 1 error. So the mistake of rejecting the null hypothesis when it's actually true. So the symbol alpha is used to represent the probability of a type 1 error. Doop-a-doop-doop. And then type 2 error, mistake of failing to reject the null hypothesis when it's actually false. So type 1 errors, we reject the null when it's true. Type 2 is we don't reject it when we should. Symbol beta is from this. So a decision, so the null hypothesis is true. Our decision is we decide to reject the null hypothesis. That's a type 1 error, rejecting the true null hypothesis. If the null hypothesis is false and we decide to reject the null, that's correct. If the null hypothesis is true and we fail to reject the null, that's what we should do. And then type 2 is over here. The null hypothesis is false and we fail to reject it. So we accept it when we should because it's false. So that's a type 2 error. And that brings us to the end of the section.